Hello, my dear students. Welcome to ESR Chemistry classes. Here we are in lecture number 10 on ESR spectroscopy applied to inorganic chemistry. In this video, we will continue our discussion on zero field splitting. First of all, let us recapitulate the discussions in the previous video. This figure was shown in the previous video. If there is no magnetic field, S equals to one state remains singly degenerate. But when an external magnetic field is applied, three orientations of resultant spin angular momentum vector in the space are possible. Sz equals to -1, Sz equals to 0, and Sz equals to +1. And according to the selection rule, delta Sz equals to ±1, true transitions are possible among these three energy states A and B. The S equals to 1 of a molecule or ion having two unpaired electrons can have three orientations in the presence of an external magnetic field, among which two transitions of same energy A and B involving delta Sz equals to ±1 are possible, and just one spectral line is expected. These two transitions from Sz equals to -1 to Sz equals to 0, that is A, and Sz equals to 0 to Sz equals to +1, that is B, involve delta Sz equals to +1. And these two transitions require the same amount of energy, and hence just one spectral line is expected in the ESR spectrum of such systems, such molecules or ions having two unpaired electrons. But it is not true. In fact, two spectral lines with different energies are observed in almost all the cases. It means the energy levels are split up unsymmetrically rather than symmetrically. It can be explained as follows. Each S equals to 0 state is made up of two electrons with each S equals to one state, not 0. Each S equals to one state is made up of two electrons with parallel spins. Each electron spin produces a magnetic field near its partner. Each electron spin produces a magnetic field nearby or in the vicinity of its partner. The up spin, that is the electron with alpha spin, increases the neighbor's magnetic field. The electron with up spin, that is the electron with alpha spin, having ms equals to +12, increases the neighbor's magnetic field. On the other hand, the electron with down spin, the electron with beta spin, having ms equals to -12, decreases the neighbor's magnetic field. It can be explained with the help of diagram as follows. It represents Sz equals to +1. It consists of two electrons P and Q having parallel spin with ms equals to plus half. This also has ms equals to plus half. Thus, both the electrons have up spin or alpha spin. As our previous discussion, this electron q with up spin increases the magnetic field in the vicinity of its neighboring electron, and therefore the magnetic field experienced by this electron is increased by q, by this electron. Similarly, the magnetic field experienced by electron q is increased by electron p, because both the electrons have up spin, both the electrons have alpha spin having ms equals to plus half, and they increase the magnetic field in the vicinity of their neighboring electron. As a result, both the electrons feel magnetic field greater than the applied magnetic field. Two electrons of Sz equals to plus 1 state feel a magnetic field greater than the applied magnetic field. Similarly, let us consider Sz equals to minus 1 state. It consists of two electrons R and S having down spin, that is beta spin, with ms equals to minus half and ms equals to minus half. We have seen earlier that the electron with down spin decreases the magnetic field experienced by its neighboring electron, and therefore the magnetic field experienced by electron R is decreased by electron S. Similarly, the magnetic field experienced by electron S is decreased by electron R, and hence both the electrons in Sz equals to minus 1 state feel magnetic field smaller than applied magnetic field. Both the electrons in experience magnetic field greater than applied magnetic field, while in Sz equals to minus 1 state both the electrons experience magnetic field greater than smaller than applied magnetic field. As a result, both the spins in Sz equals to plus 1 state feel an applied magnetic field greater than external magnetic field. If we apply an external magnetic field Bz, both the electrons of this energy level experience a magnetic field greater than this value. It is called dipolar coupling or dipolar interaction. It increases the energy of Sz equals to plus 1 state. We have already seen that the energy of Sz state increases with increase in the strength of applied magnetic field, and since both the electrons of this state experience greater increased magnetic field, and hence the energy of this state increases. Similarly, both the spins in Sz equals to minus 1 state experience an applied magnetic field greater than the external magnetic field Bz. Both the electrons of this state has down spin, and they decrease the magnetic field experienced by the neighboring electrons, and hence both the electrons of this state experience a local magnetic field smaller than external magnetic field. It again raises the energy of Sz equals to minus 1 state. Remembering that the energy of Sz equals to plus 1 state increases while the energy of Sz equals to -1 state decreases with increase in the strength of applied magnetic field. We have already seen that the energy of Sz equals to -1 state decreases with increase in applied magnetic field, while the energy of Sz equals to +1 state increases with increase in the strength of applied magnetic field. Since the magnetic field experienced by electrons in Sz equals to -1 state is lower, the magnetic field strength is lowered at higher magnetic field. This is the energy of Sz equals to -1, but at lower magnetic field, this is the energy of Sz equals to -1 state, and hence the energy of Sz equals to -1 state also increases. In Sz equals to 0 state, the dipolar field is across the main applied magnetic field, and therefore it neither adds nor subtracts from it. The Sz equals to 0 state has dipolar field across the main applied magnetic field, and therefore it neither adds nor subtracts from it, and hence the energy of Sz equals to 0 state remains unaffected or constant by dipolar coupling. Due to dipolar coupling, the energy of both Sz equals to +1 and Sz equals to -1 states increase. The net effect of this dipolar interaction is that the energies of both Sz equals to +1 and Sz equals to -1 states increase with respect to the energy of Sz state. The net result of dipolar coupling or dipolar interaction is that the energies of both Sz equals to +1 and Sz equals to -1 states increase with respect to the energy of Sz equals to 0 state, and this increase in energy is called dipolar shift, and it is denoted by D. It must be noted that the dipolar shift, that is D, is smaller than the splitting caused by the main applied magnetic field. The dipolar shift has a smaller value than the splitting caused by the main applied magnetic field. Let us see the diagrammatic representation. This is Sz equals to +1. It is singly degenerate if there is no applied magnetic field. It splits up into 3 energy levels: Sz equals to -1, Sz equals to 0, and Sz equals to +1 in external magnetic field. And according to the selection rule, delta Sz equals to ±1, 2 transitions A and B are possible among these 3 spin energy levels. Both these transitions require the same amount of energy, and hence a single absorption line is expected in the ESR signal. But it is not true. Invariably, 2 spectral lines are obtained. It has been explained with the help of dipolar shift. We have discussed already that the energy of both Sz equals to -1 and Sz equals to 1 +1 states increase with respect to the energy of Sz equals to 0 state. The energy of this state increases by an amount d, and the energy of Sz equals to plus 1 state also increases by an amount d due to dipolar coupling or dipolar interaction, which is produced by magnetic field caused by an unpaired electron in the vicinity of its neighboring electron. Now the transitions among these three energy levels, Sz equals to minus 1, Sz equals to 0 and Sz equals to plus 1, involving delta Sz equals to plus minus 1, are represented by C and D. Now it is evident that the transition C requires lower amount of energy, while the transition D requires higher amount of energy, and hence two spectral lines are expected in the ESR spectrum. Here it is a noteworthy fact that the dipolar shift D is smaller than the splitting caused by the main magnetic field. This value is smaller than the splitting caused by the main magnetic field. The magnitude of dipolar shift, that is D, is quite independent of the applied magnetic field. Capital D does not depend upon the magnitude of applied magnetic field because this dipolar shift is caused by electron-electron coupling. In order to understand the dipolar shift, we can assume that the energies of Sz equals to plus 1 and Sz equals to minus 1 states are above Sz equals to 0 state. To the same extent, even in the absence of external magnetic field. In order to explain dipolar shift, we can assume that the energies of both Sz equals to plus 1 and Sz equals to minus 1 state are above Sz equals to 0 state to the same extent even in absence of magnetic field. And since S equals to 1 state has splitted into two energy levels, it is even in absence of magnetic field, it is known as zero field splitting. A splitting produced in absence of magnetic field is known as zero field splitting. The zero field splitting has been illustrated in the left hand side A of the following figure. Let us see. The energies of Sz equals to plus 1 and Sz equals to minus 1 states are above Sz equals to 0 energy level even in absence of applied magnetic field, and it is known as zero field splitting. This portion A of the figure represents zero field splitting. And when magnetic field of increasing strength is applied, the energy of Sz equals to Z remains constant. It does not change because it is across the applied magnetic field. Because it is across, the energy of Sz equals to minus 1 state goes on decreasing with increase in strength of magnetic field, while the energy of Sz equals to plus 1 state goes on increasing with increase in the strength of external magnetic field. It means as the energy of external magnetic field increases, these two states diverge. These two states diverge from one another. We know that in ESR spectroscopy, Microwave radiation with fixed frequency is used, whose energy is also constant. Let this be the energy of microwave radiation used in ESR spectroscopy. This amount of energy of microwave radiation is constant. By absorbing this radiation, by absorbing this amount of energy of microwave radiation, transitions from Sz equals to -1 to 0 and from Sz equals to 0 to Sz equals to +1 are possible. By this amount of energy, the transition from Sz equals to -1 to Sz equals to 0 can be caused at this applied magnetic field. At this applied magnetic field, the transition from Sz equals to -1 to Sz equals to 0 can take place. But by using this amount of energy of microwave radiation, the transition from Sz equals to 0 to Sz equals to +1 is not possible at this applied magnetic field, because here this energy difference, the energy required for transition, is greater than the energy of microwave radiation, and therefore the transition from Sz equals to 0 to Sz equals to +1 state is possible at lower magnetic field. Here it is possible here by absorbing this amount of energy of microwave radiation, and thus the transitions E from Sz equals to -1 to Sz equals to 0 and F from Sz equals to 0 to Sz equals to +1 take place at different applied magnetic fields, and therefore two signals are two lines, not two signals, two lines are obtained in the ESR signal of such system having two unpaired electrons, and these two lines constitute fine structure in the ESR signal. When gradually increasing magnetic field is applied to the crystal having two unpaired electrons, the levels, constant levels Sz equals to +1 and Sz equals to -1 diverge gradually. As a result, for a given radiation frequency, that is for a microwave radiation with given energy, the transitions E Sz equals to -1 to Sz equals to 0 and Sz equals to transition F from Sz equals to 0 to Sz equals to +1 will take place at different applied magnetic fields as discussed earlier, as shown in the right hand side B of the above figure. These two transitions involving delta Sz equals to +1 will take place at different applied magnetic fields for the given amount of energy of microwave radiation. Thus, ESR spectrum will consist of two lines, two fine lines. It is called fine structure, not hyperfine structure of ESR spectrum. It arises due to electron-electron coupling. The ESR spectrum of a molecule or ion having two unpaired electrons consists of two fine lines. It is called fine structure of ESR spectrum, and it arises due to electron-electron coupling. Please remember that hyperfine lines are obtained, hyperfine structure is obtained in ESR spectrum due to electron nucleus coupling, while the fine spectrum is obtained, fine structure in the ESR spectrum is obtained due to electron-electron coupling. The zero field splitting is generally a large effect. For example, the separation between Sz equals to 0 and Sz equals to plus minus 1 states in the triplet state of naphthalene is about 3000 megahertz. The difference between Sz equals to 0 and Sz equals to plus minus 1 states is 3000 megahertz in the case of naphthalene, which is comparable to energy separation of 8000 megahertz for an external magnetic field of 0.3 Tesla. These two values are comparable. Some transition metal ions exhibit much larger zero field splitting. The field sweep spectrum is shown on the bottom of above figure. It has been shown below here also. This is the fine structure in ESR spectrum of a molecule or ion having two unpaired electrons. This ESR spectrum consists of two fine lines. The separation between two fine lines is 0.1 to 0.2 Tesla. These two fine lines are separated by a magnetic field of 0.1 to 0.2 Tesla, which is much greater than the line width. This line width is generally in the range 10 to the power minus 3 to 10 to the power minus 4 Tesla. Line width is much smaller than the separation between these two fine lines, and therefore these two fine lines are separated from one another significantly. These two fine lines are observed invariably with significant separation between them, that is from 0.1 to 0.2 Tesla. Thank you for watching the video with concentration. Please like and share it, and if you have not subscribed by channel 8, please subscribe it so that you may get information regarding my new videos in time. Thank you again.